All right, number 4, first in the lineup of sample problems. And number 4 is asking, is this thing here what we call an ordered triple? If it were in 2 variables, it would be an ordered pair, but this is 3, this is an ordered triple. Is this a solution to the system? Which, just like a system in 2 equations and 2 variables, it just means, does this x, y, and z work in this equation and this one and this one? We're just going to do one of these because it's kind of a tedious process, and just a way to show what a solution is. So we'll plug in these values: 4 times -1 for x, minus y, which will be -2, plus 3 times z, which is 5. What does that equal? Well, that's -4 plus 2 plus 15. Okay, and -4 plus 2, that's a net -2. And -2 plus 15 is 13. So that checks out. Let's try the red one. Again, -1 for z, or for x, plus a -2 for y, plus 5 for z. And -1 plus -2 is -3, plus 5 would be 2, so that checks out. And the third equation, -1 plus 3 times -2 minus 2 times 5 equals -1 minus 6 now. So it's -1 minus 6 is -7. Minus 2 times 5 is 10, so -7 minus 10 is -17. And that one checks out. So, yes, it is a solution. This right here is a solution to the whole system. And now we'll go on to number 10. So number 10 starts our actually solving these systems. And a really easy method, which is outlined in your book, is let's take what is kind of new, the new thing being 3 variables and 3 equations, turn it into something we've seen before, which is 2 equations and 2 variables, and use that to progress along. To do that, I think the simplest thing to do is to eliminate one of the variables by elimination, adding 2 equations together to cancel out a variable. And then, cancel out the same variable twice, and you'll get 2 equations with 2 unknowns. So I'll show you what that looks like. I'm looking for one of these variables, either x, y, or z, that I can cancel out. So let's just go with what seems obvious. This x and this -x. It seems pretty obvious to me. It jumps out that if I add this x and this -x, they're going to cancel out. So then we'll wind up with an equation with just y's and z's as variables. So let's do that. Let's add these together. Maybe it'd be helpful, sorry about that, to label these, like equation 1 and equation 2 and equation 3. So we're going to take equation 2 plus equation 3, and these x's will cancel out. Alright. And so what we'll get is -x plus x is 0x, 2y plus 4y is 6y, -4z minus 6z is -10z, and 5 minus 1 is 4. Alright, so now we have an equation that just has y and z in it, and no x. And that's what we were used to in the previous section. We would have a y, or an x and a y, and that was it. And then we would use substitution or elimination and solve for both of them. So now what we need to do is cancel out, now that we've chosen x, cancel out x again in some other way, with a combination of 2 other equations. As long as we don't use 2 and 3 together again, we can use 1 and 3 or 1 and 2. to cancel out x again and get another equation that has a y and a z. So what I'm seeing here, since we're going for x, I see this is negative, this is positive, this just needs to be multiplied by 2, and then this will be a negative 2x. So I'm going to take equation 1 and add it to 2 times equation 2. I'm going to take 1, then I'm going to multiply equation 2 by 2 and add it to equation 1. It'd probably be helpful just to write that down. So we have 2x minus y plus 2z equals negative 7. And then when we multiply this by 2, what we'll get is negative 2x plus 4y plus negative 8z equals 10. A common mistake is when you're doing all these steps is to not multiply this by 2. That just gets missed for some reason. It's probably the most commonly missed thing. So we'll add these together now. 2x minus 2x is 0x. 4y minus y is 3y. 2z minus 8z is negative 6z. And 10 minus 7 is 3. Okay. So what we have now is an equation with y and z, and a second equation with y and z. So now we have a system of equations that is 2 equations and 2 variables. I'm just going to put this down here so we can see. Okay. Now we want to cancel one of these out, the y or the z. And I can see that 3 is just needs to be multiplied by negative 2, so it'll cancel out with this positive 6. So I'll just say times negative 2. That doesn't look like that's what I'm saying. Just multiply it by negative 2. That might get the point across. So multiply this thing by negative 2. 3 times negative 2 is negative 6y. Negative 6z times negative 2 is positive 12z, and this will be negative 6. Alright, and 6y minus 6y is 0y, negative 10z plus 12z is 2z, and 4 minus 6 is negative 2. Alright, now probably the hardest part of this whole thing is now done. We have found that z is negative 1. Now that we know that z is negative 1, we can choose either this equation or this one or this one. It doesn't really matter. Any of these that has y and z in it, we plug in z and we can find out y. So when we use this equation here, so we have 3y minus 6 times negative 1 equals 3. So that negative 1's going in for z into this equation right here. And next, we get 3y plus 6 equals 3, 3y equals negative 3, y also equals negative 1. And lastly, we have z and we have y. We can put it into one of these equations that has x, y, and z in it, and then solve for x. I'm going to use this equation right here. So x plus 4 times y, which is negative 1, minus 6 times z, which is negative 1, equals negative 1. So x minus 4 plus 6 is going to be 2. X plus 2 equals negative 1, and x equals negative 3. So the final answer is all three of these, x, y, and z. Negative 3 for x, negative 1 for y, and negative 1 for z. Okay, I keep pausing the recording of this video to write down these systems so that you don't have to sit there and watch me do the whole thing. It takes a while. Something to think about, though, when you're doing your homework and you're writing these down. I go through each of these, I write them down. As I'm writing them, I'm double-checking them, and when I get done writing the whole thing, I check again just to make sure I didn't accidentally look at number 10 when I was trying to write down number 11, make sure I didn't accidentally write a negative when it should have been positive. The smallest mistake can it makes it a completely different problem. You won't get the right solution. And then you'll sit there wondering why, and you'll find out it was this little mistake at the beginning. You have to start all over again. And if you have to start all over again, really, it's not that big of a deal. You got to change a sign here or there. A little bit of the arithmetic is different, and but you don't want to have to do that. You'd like to avoid it if possible. Anyway, there you go. So, so number 11, we're going to, again, label each of the equations, 1, 2, and 3. And again, we're going to find a variable, eliminate it, get rid of it, and do that 2 different times, so that now we have this new equation, or new system of equations that's 2 equations and 2 unknowns. So we can choose x, y, or z. It doesn't matter. And since we need to do it twice, it's nice to choose ones that that look similar, like 6, 3, and 2. It's like a little family there. 2 and 3 are factors of 6. It's going to be easy to get these to relate to each other. The y's are going to be pretty easy because these y's are just there's just 1's in front of them. I wouldn't choose the z's to eliminate first because you could multiply this 2 by -2 and get a -4z, and that would cancel those out. But then you got this 3 here, and that's not easy to work with. If you're going to eliminate it here, you'd have to turn them both into 12s or turn these both into 6s. So I would not choose z. Probably go with the y's, since I don't know, I just would. So the easiest one would be this first and this third equation. Just make one of these y's a positive y, and then you can cancel it out. And to do that, you would just take, let's see, just take -1 times, say, equation 1, and let's write down what that would be. That just changes all of these to the opposite of what they are. So -3x plus y minus 2z equals -4. Okay. And then I would add equation 2. Okay, and equation 2 is just exactly what we see there. Oh no, sorry. Not equation 2. Equation 3. That's what we had decided on. So equation 3 is 2x minus y. That's what we want. We want these to be opposites of each other and to cancel out when we add the equations together. Okay, so we get 2x minus 3x, that's -x. Y minus y is 0y. 3z minus 2z is a positive z. And 10 minus 4 is 6. So that's good. It's a pretty simple equation. We got -x plus z is 6. Now if we had another equation that was x and z and some other number, then we could eliminate something, and we'd be one step closer. So to get another equation that has only an x and a z, we need to cancel out a y, and I'm going to choose to use, say, the second and a third equation. It's going to be really easy to turn this guy into a positive 2 to cancel out with this -2. So I'll use equation 2 just the way that it looks without any changes, and that's 6x minus 2y plus 4z equals -8. And then we're going to use equation 3, but we're going to change it a little bit. We're going to change it so that this y will cancel out with this y term. And we need this to be a positive 2y, and it'll cancel out with a -2y. So we need to multiply this equation by a -2 so that this will be a positive 2. Okay, so -2 times equation 3, and that will give us a -4x and a positive 2y and a -6z and a -20. Alright, 6x minus 4x is 2x. -2y plus 2y is 0y. That's just what we wanted. -6z plus 4z is -2z. And that equals -28. So now we have an equation with an x and a z, and another one with an x and a z. And so now we need to solve this system here. I'll make these purple equations 1 and 2. So I think what I'll do is take this x, I'll multiply, well, we'll have to do the whole thing, but I want this to make this a negative 2, and then it'll cancel out with this positive 2. So I will take 2 times equation 1, and that will give us negative 2x plus 2z equals 12. And I will just add equation 2 just the way it is. We get a positive 2x minus 2z equals negative 28. All right. Negative 2x plus 2x, 0x. 2z minus 2z, 0z. So on this side we have nothing. We have 0. On this side we have 12 minus 28. And this is negative 12, negative 18. No, negative 16. Let's see. Sorry. Anyway, I just went off on my own mind tangent. So 0 equals negative 16. That is never true. There's nothing that we can do about it. We can't make it be true because we have no x's or z's left to do anything to this equation. It just says 0 equals negative 16. So this system, the way it's written, produces this 0 equals 16, which is false. This can never be. And we can never change it. So this is a statement that's always false. This system just can't be solved. So there's no solution. It's impossible to solve this system. So it's the same as with the system of 2 equations and 2 unknowns. If we get a false equation at the end, then we have no solution. Okay, and we're going to skip this the section in your homework set. Well, I guess your homework set is the set of problems I've assigned, and I won't assign the substitution method because I think it's a terrible idea to use substitution. I don't even really like substitution unless it's really clear-cut and simple on 2 equations and 2 unknowns, but with 3 equations and 3 unknowns, it's incredibly tedious and ridiculous, and I don't think we should do it. Just because we can doesn't mean we should. So yeah, that's it. So now we have 25, and this says use any algebraic method we want, meaning substitution or elimination. And since I clearly don't like substitution for 3 equations and 3 unknowns, we're going to use elimination again. All right, so I think this is working nicely to label these equations. Equations 1, 2, and 3. Let's eliminate a variable twice, and then keep going from there. So we're looking, this is not going to be a happy ending. 5, 2, and 7, these do not share factors. It's not going to be easy. 2z, 1z, 3z, these could work. We could manipulate this z easily since it's just a 1z. We could multiply it by a 2 and then by a negative 3. But the x's for this one, they're already opposites in equation 1 and 2, so we might as well, that work is done for us, so we might as well do that. And since it's pretty straightforward, I'm not going to rewrite those ones. Just going to add them together. X minus x is 0x. 5y minus 2y is going to be 3y. Negative 2z plus z is negative z. And 6 minus 1 is 5. Okay, so we've got one equation there. Now, we got a negative 2x. We need a positive 2x to cancel out with it, so we'll use this positive x, and we'll just multiply it by 2. Okay, so we'll take negative 2 times equation 1. No, not negative 2, positive 2. Positive 2 times equation 1. And we'll get 2x, it's 2x plus 10y minus, this will make it a 4z, minus 4z, equals negative 1 times 2 would be negative 2. And we're just going to add equation 3. And that'll be negative 2x minus 7y plus 3z equals 7. These will cancel each other out. 2x minus 2x is going to be 0x. 10y minus 7y is 3y. 3z minus 4z is negative z. And 7 minus 2 is 5. Alright, so now we have equation 1 and 2 in purple. We need to cancel some stuff out. It looks like an equal challenge here between the 3y and the negative z. So we'll just make one of these negative. We'll make this a negative 3y, and this will be a positive 3y, and they'll cancel out. So we'll do negative 1 times equation 1. And this will give us negative 3y plus z equals negative 5. And then we're going to add equation 2, purple equation 2, and we'll have 3y minus z equals 5. Right, so negative 3y plus y, that's going to be 0y. Z minus z is 0z. We have nothing over here. And negative 5 plus 5 also gives us 0. This is just like the one we just did here. We wound up with 0 equals negative 16, except instead of being false, this is true. So where in this one we could do nothing about the falseness of this equation, like the x and the z disappeared, and there was nothing we could do to make this true. There's nothing that we can do to make this equation false. There's an infinite supply of ordered triplets that we can plug in for x, y, and z in all three equations and get all three equations to be true. Okay, so this would be an infinite number of solutions. Right. So now I don't know what the graph would look like, but in the intro video we talked about it could possibly look like two of these planes, right? That's the graph of three variables. Could come together like a folded piece of paper. They could just meet like that, making a line, and then the third plane could be like what these two planes are resting on top of, if you could imagine that. So they could possibly have that as infinitely many solutions, or they could just be there's one plane, there's the second one in the exact same place, and the third one again in the exact same place. They could have all three of the planes could be the exact same thing, and that's why there's an infinite number of solutions. Whatever the case, that's what we have, an infinite number of solutions. You don't have to know what the graph looks like. That's not our concern, just finding the number of solutions. Okay, so that's number 25. We'll go on and do number 35, but I'll pause the video for a second. Okay, now the reason I brought this up is because it has fractions. Fractions scare some people, and we want to get rid of that phobia. To get rid of these fractions and make this a less complicated problem is quite simple, really. We are really familiar with multiplying these equations by numbers, so that part of it is really helpful. I'm just going to suggest an idea. If we again label these 1, 2, and 3, what would happen, just suggesting that we multiply this equation by 2. 2 times equation 1. What will happen then? We'll multiply x by 2, we'll get 2x. Now we're going to multiply this by 2. 2 times a half, well, the 2 times 1/2 would, the 2 and the 1/2 would cancel each other out. So what we'll get is just y. Again, if we multiply 1/2 by 2, 2 and 1/2 cancel each other out to 1, and now we're just left with z. And if we multiply 5/2 by 2, I'll come over here real quick, 5/2 times 2, and we could write this as 2 over 1, that's helpful. And when we multiply fractions, we can cross cancel. This is 1 and 1. So 1 times 5 over 1 times 1, that just leaves 5. So what we did there was to multiply it by a number that will cancel out these denominators, and we have no more denominators. So it turns the denominators into a 1. because of cross-canceling. So what would do that in this equation? Well, certainly if we multiplied this one by a 2, the same thing would happen as happened over here, and we would get basically just the numerator, the 3. But if we multiply this by a 2, it's just going to cancel out a single factor of 2 here in the denominator, and we'll still be left with the denominator of 2. So how about if we multiply this by something that has factors of all the denominators? It has a factor of 2 and a factor of 4, and, well, we don't need to include these. These are the same, 4 and 4 and 4. If it cancels out this 4, when you distribute it to here, it'll cancel out this 4, and so on. So what if we used 4? Because 4 has a factor. This is 4 times equation 2. 4 has a factor of 4 and a factor of 2, so when we distribute it to each of these, it should cancel out all the denominators. If we multiply this by 4, the same thing happens as happened over here, and we'll cancel out the denominator of 4 and be left with 3, so 3x, plus, now we'll cancel out the 4 and be left with 1 times y, plus, now, let's come over here, 3 halves times 4, or 4 over 1. These two can cross-cancel. This becomes a 1, this becomes a 2. So now you have 2 times 3, and that's 6z. And on this side, we're multiplying this by a 4 as well. Cancels out the 4, we're left with 7. All right, equation 3, what should we do to that? We want to cancel out a 3, right? So we're going to need to have whatever we're multiplying have a factor of 3, also a factor of 2. Okay, factor of 3 again, that's fine. That's the same number that works for this one should work for this one, and a factor of 6. So it has a factor of 6 and 3 and 2. 6 does. 6 has a factor of 6 and a factor of 3 and a factor of 2, so we'll multiply equation 3 by 6. So it's going to happen there. So we're going to multiply 6, let's say 6 times 1/3. We could think of it as 6 over 1. Cancels 3 and 6, this becomes 1, this becomes 2. Oh, sorry, when you cancel out this factor of 2 in 6, this will be 3. You may have caught that, so that'll be 9. So it'll be plus 9y. Plus, now let's take 6 over 1 times 2/3. Cancel out the factors of 3, this will be 2. 2 times 2 is 4. That'll be plus 4z equals 6 times 13 over 6, so it'll just cancel out the 6's and we'll be left with 13. Okay, and we'll just leave it at that. It's just another system. We've done a few examples of solving systems, and you could take this, if you were to do this on your own, I would suggest starting with these y's, cancel those out, and then use one of them to cancel out this 9y, and you'll have two equations with x and z in them. But the point of that, it was just to see that you could get rid of those fractions and make it into just a normal looking system. Alright, so now let's move on, if the computer will let us, to number 42, which involves a pizza, soda, and salad. And we're going to create our own system of 3 equations and 3 unknowns. So let's see. 2 small pizzas, a liter of soda, and a salad cost $14. You can see different combinations of pizza, salad, and soda cost different amounts of money. And at the end, what is the cost of 1 small pizza, a liter of soda, 1 salad? So apparently our unknowns are going to be the cost of each of these things. So x could be the cost of a pizza, y could be the cost of a single soda, and z could be the cost of a salad. So it's saying that 2 small pizzas, so 2 times small pizza, and a liter of soda, so just 1 liter of soda, and a salad plus 1 salad is equal to $14. A different combination, 1 small pizza, a liter of soda. And 3 salads costs $15. And the third, 3 small pizzas, see, 3 small pizzas and just a liter of soda with no salad costs $16. So how much are x, y, and z basically? Well, we have this equation that has an x and a y and no z, so we may as well cancel z out, and we'll have another equation with just an x and a y, and that should be pretty straightforward. So if we call this equation 1, equation 2, and equation 3, then we want to cancel out the z's. If this were a negative 3z, then it would cancel out nicely, so we'll multiply this by a negative 3, which means we have to multiply the whole equation by a negative 3. So negative 6x minus 3y minus 3z equals negative, let's see, 52, 42, 42. Then we'll just add equation 2. And that is x plus y plus 3z equals 15. That'll be 6 minus 6, or negative 6x plus x is negative 5x. Y minus 3y is negative 2y. 3z minus 3z is 0z. And 15 minus 42 is negative 27. All right. So now we have this equation and this equation both with just an x and a y. So we have 3x plus y equals 16. That's from here. And negative 5x minus 2y equals negative 27. That's from right there. And so we want to cancel out something here. It's equation 1 and equation 2. Looks to me like the y's would be the easiest thing to cancel. I would just take 2 times equation 1. That's going to be 6x plus 2y equals 32. And then just add equation 2. And equation 2 is just negative 5x minus 2y equals negative 27. 6x minus 5x is x. 2y minus 2y is 0. And 32 minus 27 is 5. So x is 5. So the cost of a pizza is $5. So if x is 5, let's put that in here to this equation. Let's use this color here. So 3 times 5 plus y equals 16. So 15 plus y equals 16, and y equals 1. So there's x and there's y, and now we need to find z. Let's just put x and y into this equation. This is just there. So 2 times x, which is 5, plus y, which is 1, plus z is 14. That's an arrow pointing this way. That's 10 plus 1, that's 11, plus z equals 14, so z equals 4. Okay, so the cost of a single small pizza is $5, the cost of a liter of soda is $1, and the cost of a salad is $4. All right, thanks for hanging with me through all that, and I hope that was helpful.